Hello students, welcome to my new video of describing some probable questions from physical chemistry for NEET JEE aspirants. First a statement question from thermodynamics. Statement 1. During ideal gas isothermal reversible expansion, the work involved is a maximum. Statement 2. During ideal gas isothermal reversible compression, the work involved is a minimum. Are these statements correct or not? The answer is both statements are correct. And a student need study this conclusion as such. Student need not worry about how these conclusions came. But an inquisitive student may want to know why the results are so, and hence this video. To grasp the explanation of these conclusions, one requires a previous knowledge of 3 or 4 facts. Number 1, the pressure-volume relation as implied in Boyle's law. Pressure is inversely proportional to volume. For a given amount of gas, constant amount, number of moles, and constant temperature, the pressure volume graph looks like graph 1. Pressure decreases with increase of volume in this particular graph style. This type of graph is called a rectangular hyperbola. From A to B, it represents expansion of the gas. From B to C, B to A, it is compression. Any initial state is indicated by subscript 1 and final state 2. To avoid confusion, the initial stage of compression is given P1, V1 written in italics, P2, V2 also in italics. Second requirement is general expression for pressure volume work. The magnitude is given by integral V1 to V2 pressure external dV. For a given initial and final state, for a given process, the magnitude of work is directly proportional to the magnitude of external pressure. Higher the external pressure, higher the work, and vice versa. Thirdly, this integral representing work is easily obtained by measuring suitable areas in the PV plots. Fourthly, reversible condition means the driving force is almost equal to the opposing force. Driving and opposing forces are almost equal. It can be taken as equal. So it is a near equilibrium process taking place extremely slowly. Whereas the irreversible path corresponds to driving and opposing force widely different. With these prerequisites, let us analyze the work of expansion. First, reversible expansion. As I said, during expansion, driving force is pressure of the gas. It will be a little bit greater than opposing force, pressure external, by an infinitesimal amount dP. For practical purposes, P gas is the same as P external. As the pressure of gas decreases in a hyperbolic style, the external pressure also decreases. And the work involved, W reversible equal to integral V1 to V2 P external, which is now pressure of the gas, PV, is the area enclosed between this pressure external hyperbolic curve, the volume axis, and the vertical lines V is equal to V1 and V is equal to V2. I have noted this area by shading the space with many vertical lines. for the irreversible expansion, the driving force is widely different from the opposing force, pressure external. Pressure external is very, very small compared to the pressure of the gas at the start. It can be as small as P2. So, all along the irreversible expansion, the external pressure remains a constant at P2, and up to the last point, the external pressure and pressure of the gas are widely different, and the process stops when the pressure of the gas also becomes P2, the external pressure. When two forces become equal, the process stops. Now, W irreversible is integral V1 to V2 pressure external, which is now equal to P2 constant dV. Being a constant, it is taken out, and integral dV is V. Applying limits, it becomes P2 minus V1. So the value of work will be P2 into delta V, which is simply the area of the rectangle of a height P2 and a width delta V. It is marked by slanting lines. Now compare the two areas marked by vertical lines and the area marked by slanting lines. W reversible is much greater than, that area is much greater than W irreversible, or reversible work of expansion is a maximum. Similar considerations apply to compression of the gas. For compression, the starting point is italics P1, V1. The volume is very large, pressure is very low. And for the reversible compression, the same condition, pressure external is now the driving force equal to pressure of the gas plus dP, or pressure external is almost the same as pressure of the gas. During compression, the pressure external increases parallel to the pressure of the gas from the point P1 up to the point P2. External pressure varies, and integral P external, which is equal to P gas V1 to V2 PV, will be, you can take the P gas outside and the integral is exactly as given in graph 2. It is the area enclosed between this hyperbolic curve, the volume axis, and the vertical lines V1 at the starting point and V2, both in italics. Same area. For the irreversible compression work, W irreversible, the driving force, pressure external is far greater than pressure of the gas. When the pressure of the gas is at V1, the pressure external is as large as P2, and it remains a constant there. So all through this compression, the external pressure remains a constant at P2. A wide difference between pressure of gas and external pressure is maintained. That is a condition of irreversibility, and it continues until the pressure of the gas itself becomes P2 equal to the constant external pressure. Now, W irreversible compression is integral P external, which is the very high pressure italics P2 into dV. This being a constant, it is taken out, so it becomes P2 into V2 minus V1, or delta V. So it is the area of this rectangle marked with slanting lines, with one side of length delta V and another side of length P2. Now compare the areas marked by slanting lines and the area marked by vertical lines. It is very clear that W reversible is far less than W irreversible, or during the reversible isothermal compression of ideal gas, the work involved is a minimum compared to the irreversible work. I hope the concepts are clear to you. See you later for another video. Thank you.